What if we're not alone in the universe? For centuries, humanity has gazed at the stars, wondering if life exists beyond our pale blue dot. And now, science is bringing us closer than ever to an answer. Across distant galaxies, within swirling nebulae, and on the surfaces of mysterious exoplanets, astronomers are uncovering clues that could rewrite our understanding of existence itself. Imagine standing at the edge of a cosmic revolution, where every new discovery whispers the possibility that we're part of something far grander than we ever dreamed. This isn't just science fiction anymore. Over the past few decades, cutting-edge telescopes, daring space missions, and brilliant minds piecing together the puzzle have revealed 30 astonishing cosmic discoveries, each one a potential key to unlocking the mystery of life beyond Earth. From water vapor plumes erupting on icy moons to eerie radio signals repeating from deep space, these findings aren't just fascinating, they're reshaping the very questions we ask about our place in the universe. And the most thrilling part, we're only just scratching the surface, so buckle up because today we're diving into the most compelling evidence ever gathered, phenomena so strange, so unexpected. They've left even the most skeptical scientists questioning what's really out there. Whether it's organic molecules floating in the atmosphere of distant worlds or bizarre structures that defy explanation, each discovery brings us one step closer to answering humanity's oldest question: are we alone? Get ready to explore the cosmos like never before, because what you're about to witness could change everything you thought you knew about life, the universe, and our tiny, extraordinary corner of it. The journey starts now. Picture a planet shrouded in thick, acidic clouds where surface temperatures could melt lead, an environment so hostile, it seems like the last place we'd ever expect to find signs of life. Yet in 2020, astronomers made a jaw-dropping announcement. They detected phosphine gas in the upper atmosphere of Venus. Now, why is that such a big deal? On Earth, phosphine is almost exclusively produced by living organisms, tiny microbes thriving in oxygen-free environments like swamps or even animal intestines. It's not something that forms easily through ordinary geological or chemical processes. So when scientists spotted its spectral signature floating 40 miles above Venus' scorching surface, it sent shockwaves through the scientific community. This wasn't just a curious anomaly, it was a potential biosignature, a molecule that could hint at life clinging to existence in those swirling, sulfuric clouds. The discovery forced us to rethink everything we thought we knew about Venus. Sure, the planet's surface is a hellish nightmare, but up in the clouds, temperatures and pressures are surprisingly Earth-like. Some researchers even proposed that microbial life could survive there, drifting like extremophile sailors on an alien sea of droplets. But here's where things get messy. Almost immediately, other teams questioned the findings. Could there be some unknown chemical process on Venus, a trick of geology or atmospheric reactions we don't yet understand, that's creating this phosphine without life? The debate raged in labs and conference halls, with studies alternately supporting and refuting the original detection. What makes this discovery so electrifying isn't just the possibility of life next door, it's how it exposes the gaps in our knowledge. Venus was right there all along, hiding mysteries in plain sight. If life really exists in those clouds, it would mean habitable zones around stars are far more flexible than we ever imagined. And if it's not life, well, we've still stumbled upon some bizarre, unexplained chemistry happening on our planetary neighbor. Either way, Venus just became a lot more interesting, and the hunt for answers is far from over. The idea that life could be floating in Venus clouds isn't as far-fetched as it might seem. If we look at Earth's own extremophiles, organisms thriving in places we once thought were uninhabitable. Here on our planet, microbes survive in boiling volcanic vents, radioactive waste, even the vacuum-like dryness of the Atacama Desert. So why couldn't life adapt to Venus' upper atmosphere? The clouds themselves might be acidic enough to dissolve metal, but at around 30 to 40 miles above the surface, temperatures hover between 30 and 70 degrees Fahrenheit, comfortably within the range some Earth microbes call home. And while the air pressure isn't identical to ours, it's not the crushing, bone-shattering force found at Venus' surface. Scientists have even proposed a tantalizing life cycle for these potential Venusian microbes. Picture this: tiny organisms suspended in droplets, metabolizing sulfur compounds or other chemicals in the thick atmosphere. As the droplets grow heavier, they sink into the hotter layers below, but before they get too deep, intense sunlight might evaporate them, releasing the microbes back into the upper atmosphere like microscopic phoenixes rising from the acid. It's a wild theory, but one that takes inspiration from Earth's own resilient life forms. There's precedent for this kind of adaptation. Bacteria like Acidotheobacillus thrive in sulfuric acid environments, and some species even produce phosphine, just like the gas detected on Venus. But of course, extraordinary claims require extraordinary evidence. Critics point out we still don't fully understand Venus' atmospheric chemistry. Could there be unknown reactions creating phosphine without life? Lightning, volcanic eruptions, or even solar wind interacting with the planet's unique atmosphere might produce the same signature. Even if microbes aren't the explanation, this discovery has already shifted how we think about habitability. Life might not need a cozy Earth-like planet. It could be hanging on in the most unexpected places, forcing us to expand our search beyond the traditional Goldilocks zone. Venus, once written off as a lifeless inferno, might just hold the first clues to a radical new understanding of where life can exist. While Venus teases us with its acidic mysteries, Mars has been playing an equally enigmatic game, this time with a gas that's intimately linked to life on Earth. Since 2012, NASA Curiosity rover has been sniffing the thin Martian air, and it's picked up something startling: methane levels that rise and fall with the seasons. Now, methane shouldn't be there, at least not in these fluctuating amounts. On our planet, most methane comes from living things, whether it's microbes in wetlands, the digestive systems of cows, or even decaying plants. So when Curiosity detected these seasonal spikes, scientists' hearts raced. Could this be a faint, gaseous whisper of Martian microbes burrowing beneath the rust-colored soil? The data tells a compelling story. Every Martian summer in Gale Crater, where Curiosity roams, methane concentrations climb to around 10 times their usual levels before dropping again. This pattern repeats like clockwork, suggesting an active source replenishing the gas. Even more tantalizing, some of the spikes are sharp and localized, as if the rover drove right through an invisible plume. But before we declare this proof of subterranean life, there's a twist. Mars has ways to produce methane without biology. Geological processes like serpentinization, where water reacts with certain rocks, can generate the gas. Even ancient methane trapped in ice could slowly seep out as temperatures shift with the seasons. The debate hinges on a critical question: is this methane being made now, or is it ancient gas stirring from its slumber? If it's actively produced, the door cracks open for biological explanations. Imagine extremophile microbes surviving in briny pockets beneath the surface, metabolizing carbon and hydrogen to release methane as a byproduct. But if the source is geological, we're looking at a Mars that's still chemically dynamic, if not biologically alive. The European Space Agency's Trace gas orbiter complicated things further when it failed to detect methane in Mars' upper atmosphere, contradicting Curiosity's ground-level readings. This discrepancy could mean the gas disperses quickly or that its sources are hyper-localized. What makes these methane fluctuations so riveting isn't just the what, but the where. Gale Crater was once a lakebed, a place where life, if it ever existed, might have thrived. If methane is seeping from its ancient sediments, we could be tasting the echoes of a habitable Mars from billions of years ago. Future missions like the Mars Life Explorer aim to drill deeper, literally and figuratively, into this mystery. Until then, Mars keeps us guessing, dangling clues just out of reach. Whether the answer is biology or geology, one thing's certain: the red planet still has secrets to spill. Beneath the frozen wasteland of Mars' south pole, something extraordinary lurks, not in the frigid air or the barren dust, but deep underground. In 2018, scientists analyzing data from the European Space Agency's Mars Express orbiter made a stunning announcement. They'd found evidence of a massive liquid water lake buried under a mile of ice. Unlike the fleeting hints of surface water or the seasonal methane whispers, this was a persistent reservoir spanning 12 miles across and possibly staying liquid despite temperatures that would freeze water solid in seconds on the surface. How is that possible? The answer lies in the same forces that keep Earth's subglacial lakes like Antarctica's Lake Vostok from freezing, a combination of pressure from the ice above and dissolved salts lowering the water's freezing point. This discovery flipped the script on Mars' habitability. If liquid water exists there, shielded from the harsh surface radiation and extreme cold, could it also harbor life? On Earth, subglacial lakes are teeming with microbial communities that have survived in isolation for millions of years, thriving without sunlight by metabolizing minerals and organic material trapped in the ice. These extremophiles prove life can persist in some of the most unforgiving environments imaginable. Now, picture a similar scenario beneath Mars' polar cap. Perhaps microbes evolved long ago when the planet was warmer and wetter, retreated into these hidden aquatic refuges as the surface dried up. The chemistry might not be identical. Mars lacks Earth's tectonic activity and nutrient cycles, but the principle remains: where there's liquid water, there's potential. Yet skepticism lingers. Some researchers argue the radar signals interpreted as liquid water could instead be layers of clay or highly saline slush, too thick to flow but still reflecting the orbiter's scans like a mirror. Others point out that Mars' subsurface might be too cold even for briny water to stay liquid without geothermal heat, which Mars lacks compared to Earth. But in 2020, the plot thickened when follow-up studies revealed not one, but 4 smaller lakes clustered around the original site, suggesting an entire network of underground pools. The more we look, the more Mars seems to hide its water in plain sight, or rather, just out of reach. The implications are staggering. If these reservoirs are real and stable, they could be time capsules preserving traces of ancient Martian life, or even sustaining it to this day. Future missions equipped with drills or melt probes could one day sample these buried waters, searching for microbial fingerprints. Until then, the very existence of these possible lakes forces us to reconsider where life might cling on in our solar system, not just on temperate surfaces, but in the dark, salty depths beneath them. Mars, it seems, still has oceans left to explore. They're just waiting under the ice. While Mars hides its watery secrets beneath ice, Jupiter's moon Europa wears its ocean on its sleeve, or rather, sprays it into space in spectacular fashion. In 2013, the Hubble Space Telescope caught something extraordinary: massive plumes of water vapor shooting over 100 miles high from Europa's icy crust. Think of it like a celestial geyser, erupting with such force that the material reaches heights 7 times taller than Mount Everest. These aren't just random spurts. Hubble detected them multiple times near the moon's south pole, hinting at an ongoing process beneath that frozen shell. What makes these plumes so electrifying is what they imply about Europa's hidden depths. Scientists have long suspected the moon harbors a vast subsurface ocean, kept liquid by the gravitational squeezing of Jupiter's immense pull. But these eruptions suggest that ocean isn't just sitting there. It's actively interacting with the surface, possibly even venting into space. If that's the case, we might not need to drill through miles of ice to sample Europa's waters. The ocean could literally be throwing itself at us, offering free samples of whatever. or whoever might be swimming in those alien depths, the possibilities are mind-bending. Earth's own deep-sea hydrothermal vents thrive with life despite crushing pressure and total darkness, powered by chemical energy rather than sunlight. Europa's ocean, warmed by tidal forces and potentially rich in minerals from its rocky core, could harbor similar ecosystems. Those plumes might carry organic molecules, salts, or even microbial life from the depths, frozen into tiny ice particles as they erupt into space. It's like Europa is bottling its secrets in snow and launching them into orbit, just waiting for us to catch one. That's exactly what NASA Europa Clipper mission aims to do. Slated to launch in 2024, this spacecraft will conduct dozens of close flybys, mapping the Moon's ice shell and analyzing plume material with state-of-the-art instruments. One tool, aptly named the S-Surface Dust Analyzer, will catch ejected particles and determine their composition down to molecular levels. Another, an ice-penetrating radar, will peer through the crust to measure the ocean's depth and salinity. But perhaps most thrilling, the Clipper will scout landing sites for a future mission that might finally drill, or even swim into Europa's enigmatic waters. Of course, mysteries remain. Why do the plumes only appear in certain regions? What's pumping them so high against Europa's weak gravity? Some theories suggest tidal flexing opens cracks in the ice, allowing water to burst forth like a shaken soda can. Others propose underground reservoirs of liquid water closer to the surface, erupting when pressurized. Whatever the mechanism, one thing's clear: Europa isn't a dead ball of ice. It's dynamic, alive with geological activity and possibly, just possibly, biological activity too. As the Clipper speeds toward its destination, humanity stands on the brink of answering one of science's greatest questions. Could an entire alien ocean be teeming with life just 500 million miles away? The evidence is literally spraying into the cosmos. We just have to reach out and catch it. Here on Earth, some of the most alien life forms don't live in outer space. They thrive in the crushing darkness at the bottom of our oceans, clustered around hydrothermal vents. These underwater chimneys spew superheated, mineral-rich water, creating oases of life where no sunlight ever penetrates. Entire ecosystems flourish here, built not on photosynthesis but chemosynthesis bacteria that convert chemicals like hydrogen sulfide into energy, forming the base of a food web that includes giant tube worms, ghostly shrimp, and heat-resistant microbes. It's a perfect blueprint for how life might survive in Europa's lightless ocean. The parallels are striking. Just like Earth's vents, Europa's seafloor likely has hydrothermal activity, warmed by the Moon's constant flexing under Jupiter's gravitational pull. Rock and water interact there, producing energy-rich compounds that could fuel life. Scientists estimate Europa's ocean might contain twice the volume of Earth's oceans, with enough heat and chemical diversity to support not just microbes but potentially more complex organisms. Imagine tube-like creatures anchored to Europa's underwater vents, or free-swimming life forms evolved to navigate its pitch-black waters. The conditions wouldn't be identical. Europa's chemistry might rely more on sulfur or methane than Earth's vents, but the principle remains: where there's energy and liquid water, life finds a way. What's even more compelling is how Earth's extremophiles keep rewriting the rules of habitability. Microbes called archaea thrive near our vents at temperatures above 200 degrees Fahrenheit, surviving pressures that would crush most submarines. Others, like the bone-white yeti crabs, farm bacteria on their own claws to feed in the void. If life can adapt to these extremes on Earth, why not in Europa's hidden ocean? The Moon's icy shell might even work in life's favor, shielding organisms from Jupiter's intense radiation while allowing nutrients to cycle through cracks and plumes. Yet Europa's ocean isn't just an Earth clone. Its chemistry could be far stranger. Without plate tectonics to replenish minerals, its vents might operate on longer timescales, creating ecosystems that evolve in slow motion. Or conversely, intense tidal forces might drive more violent activity, with geysers erupting like underwater volcanoes. Some theories suggest Europa's ocean floor could host cold seeps, places where methane and other gases leak slowly, supporting life forms utterly unlike anything we've seen. There's even a chance its waters are stratified, with layers of differing salinity and temperature creating isolated pockets of unique habitats. This isn't just speculation. Future missions could find answers. Europa Clipper's instruments might detect organic molecules in the plumes, hinting at the ocean's chemistry. A proposed lander mission equipped with a seismometer could listen for vent quakes echoing through the ice. And if we ever send a probe to melt through the crust, the discoveries could redefine biology itself. Whether Europa's depths hold delicate microbial mats or sprawling ecosystems, one thing's certain: the Moon's ocean is a laboratory for life's potential, testing the limits of what's possible in the cosmos. Earth's vents taught us life doesn't need sunlight now. Europa might teach us it doesn't even need a planet. If Europa has company in the cosmic hide and seek game of extraterrestrial oceans, Saturn's tiny moon Enceladus isn't just playing along, it's practically waving its secrets in our faces. When NASA Cassini spacecraft first spotted towering geysers erupting from Enceladus' south pole in 2005, scientists were stunned. This wasn't some occasional trickle. These were continuous, massive jets of water ice and vapor blasting hundreds of miles into space, creating one of Saturn's iconic rings as they froze and fragmented. But the real shock came when Cassini dove through those plumes, tasting their composition. Hidden in the icy spray, a treasure trove of organic molecules far more complex than anyone anticipated. We're not talking about simple methane or carbon dioxide. Cassini detected compounds like methanol, ethane, and even benzene rings, the kind of carbon-rich structures that form the backbone of life as we know it. Most tantalizing of all were traces of macromolecular organic material, hefty chains of carbon atoms that mimic the building blocks of proteins and membranes. These aren't just random chemicals, they're the Legos of biology, the raw materials that, given the right conditions, could assemble into something living. And where are they coming from? Deep beneath Enceladus' icy crust, where a global ocean sloshes against a rocky seafloor, heated by Saturn's relentless gravitational kneading. The implications are staggering. On Earth, hydrothermal vents on the ocean floor act as chemical factories, transforming minerals into energy-rich compounds that feed entire ecosystems. Enceladus seems to have the same recipe: water, heat, organic molecules, and a mineral-rich core. The plumes themselves might be fueled by vent-like processes, with seawater percolating through hot rock before erupting into space. Some researchers speculate these geysers could even carry microbial hitchhickers, blasting potential life forms into the void where spacecraft might easily sample them. It's as if Enceladus bottled its deepest ocean water and launched it into orbit, gift wrapped for astrobiologists, yet mysteries linger. Why are the plumes so localized at the South Pole? What's driving their incredible velocity enough to escape a moon with gravity so weak you could throw a baseball into orbit? Recent studies suggest tidally heated fractures beneath the ice, acting like subterranean nozzles that focus the eruptions. Others propose underground reservoirs of liquid water under immense pressure, exploding through cracks like champagne uncorked. Whatever the mechanism, one thing's clear: Enceladus isn't just another icy moon. It's a dynamic world with all the ingredients for life, packaged in a celestial fire hose daring us to take a sip. The Cassini mission may have ended in 2017, but its data still fuels discoveries. New analyzers continue to uncover heavier, more complex organics in the plume material, some with molecular weights in the thousands. That's the weight class of amino acids, the very stuff of proteins. Future missions like NASA proposed Enceladus Orbalander could one day orbit, and even land on this geyser-spewing moon, analyzing plume material with instruments far more sensitive than Cassini's. Imagine a spacecraft catching fresh fallen ice crystals, searching for cellular structures or metabolic byproducts. Enceladus forces us to reconsider what makes a world habitable. It's tiny, just 300 miles wide, small enough to fit within the borders of Arizona, yet it boasts more accessible liquid water than Earth's largest lakes. Its energy comes not from sunlight, but from the flexing of its core under Saturn's pull. If life exists there, it would prove that even the most unassuming corners of the cosmos can cradle biology. We used to think finding life meant finding another Earth. Enceladus suggests we should be looking for the places that defy that expectation. The small, the strange, the icy moons that turn the vacuum of space into their own delivery system for life's ingredients. Saturn's largest moon, Titan, isn't just another frozen orb, it's a bizarre, almost Earth-like world wrapped in an alien disguise. Imagine a place where rivers carve valleys into icy bedrock, where rain falls from thick orange clouds, and where vast lakes shimmer under a hazy sky. But here's the twist, those lakes aren't filled with water. They're pools of liquid methane and ethane, so cold that water is harder than granite. This isn't science fiction, it's the reality revealed by NASA's Cassini mission, which spent years peeling back Titan's secrets like layers of a cosmic onion. And what it found could rewrite the rules for where life might emerge in the universe. Titan's chemistry is a probiotic playground, a laboratory for how life's ingredients might assemble under conditions utterly unlike Earth. Its atmosphere is a thick soup of nitrogen and methane, bombarded by sunlight that breaks these molecules apart and recombines them into complex organic compounds. These molecules drift down like sticky snow, coating the surface in a layer of carbon-rich goo. Some of them form dunes as vast as the Sahara, made not of sand but of hydrocarbon grain. Others dissolve into those eerie methane lakes, creating a solvent-based chemical network that parallels Earth's water cycle. It's as if Titan took the building blocks of life and shuffled them into a deck we've never seen before. The magic happens when you consider how Titan's environment could act as a crucible for exotic biology. In labs here on Earth, scientists have recreated Titan's conditions, supercooling methane and bathing it in UV light to simulate the moon's harsh environment. The results are staggering. These experiments produce amino acids, nucleotides, and even the precursors to cell membranes, all without liquid water. Some membrane-like structures that form in these tests are startlingly resilient, able to stretch and flex in Titan's frigid temperatures. This suggests that if life exists there, it might not need the watery chemistry we're familiar with. Instead, it could rely on methane as both solvent and fuel, with cellular structures built from acrylonitrile, a compound Cassini detected in Titan's atmosphere. But the real kicker, Titan may have more in common with early Earth than we realized. Billions of years ago, before oxygen filled our atmosphere, our planet might have had methane-rich skies similar to Titan's today. Some theories suggest life here could have started in methane ponds before transitioning to water-based chemistry. If that's true, Titan might be a frozen snapshot of our own probiotic past, or a showcase for how life could evolve along an entirely different path. The methane lakes, like Ontario Lacus or Kraken-Mare, could be incubators for this alien biochemistry, sheltered beneath their icy shores. What's thrilling is how Titan challenges every assumption about habitable zones. It's far from the Sun, with surface temperatures plunging to -290 degrees Fahrenheit. Yet it's geologically active, with cryoval conos possibly spewing water ammonia slurries that could create temporary pockets of liquid water beneath the ice. Some researchers speculate about a hidden subsurface ocean, much like Europa's, where water and organics might mingle. Others imagine life forms floating in Titan's methane lakes, their metabolisms tuned to consume acetylene or hydrogen instead of oxygen. The upcoming Dragonfly mission, set to launch in 2027, will turn speculation into science. This nuclear-powered drone will hop across Titan's surface, sampling its organic-rich dunes and even touching down near a methane lake to analyze its composition. If there's even a whisper of biological activity, unusual chemical imbalances, isotopic fractionation, or complex molecules with a preferred handedness like Earth's amino acids, it could signal that life isn't just a cosmic fluke. It's a phenomenon that can bloom in the strangest gardens. Titan teaches us that life might not need Earth-like conditions, just Earth-like complexity. Wherever energy flows, solvents mix, and molecules collide, the universe seems to find a way. Whether it's in the hydrocarbon lakes of Saturn's moon or the hidden oceans of Europa, the ingredients are there. We're just beginning to learn how many recipes exist for life itself. Just 4.2 light-years away, so close that our fastest spacecraft would only need 75,000 years to reach it, Proxima Centauri b hangs in the cosmic balance, a tantalizing what-if orbiting the star next door. Discovered in 2016, this rocky world is roughly the same size as Earth and sits snugly in its star's habitable zone, where temperatures could allow liquid water to pool on the surface. On paper, that makes it one of the most promising candidates for extraterrestrial life we've ever found. But here's the catch: Proxima Centauri isn't anything like our Sun. It's a red dwarf, small and dim but prone to violent tantrums that could turn this Earth-like gem into a radiation-scorched wasteland. Let's unpack the paradox. Proxima b's orbit is tight, so close to its star that a full year there lasts just 11 Earth days. But because red dwarfs are cooler than our Sun, this snug distance still places the planet in the sweet spot where water could flow. The problem: Proxima Centauri is a flare star, frequently erupting with bursts of X-rays and ultraviolet radiation hundreds of times stronger than anything the Sun produces. These stellar tantrums bombard the planet's atmosphere, potentially stripping it away over time. If life exists there, it would need to be as resilient as Earth's toughest extremophiles, or find shelter underground or beneath thick ice. Yet hope isn't lost. Recent climate models suggest Proxima b might cling to its atmosphere if it started with a thick, protective envelope. Some simulations even show how ocean currents could redistribute heat, creating temperate zones despite the star's fury. And there's another twist: tidal locking. Like our moon with Earth, Proxima b likely has one face permanently turned toward its star, creating a blistering dayside and a frozen nightside. But in the twilight zone between these extremes, a thin band called the Terminator line, conditions might be just right for liquid water and perhaps life. The real revelation came in 2020, when astronomers detected a possible second planet in the system, along with hints of a dust ring that could signify asteroid belts or even moons. More neighbors mean more complexity and more chances for life to find a foothold. Upcoming telescopes like the Extremely Large Telescope will study Proxima b's atmosphere for biosignatures, searching for traces of oxygen or methane that might betray biological activity. If we find them, the implications would be staggering. Life not just in the universe, but right in our cosmic backyard. Proxima Centauri b forces us to rethink what habitable really means. It's a world of extremes where survival demands adaptation to relentless radiation and eternal twilight. But if life can endure there, it suggests the galaxy might be far more crowded than we ever imagined. After all, red dwarfs make up 75% of the stars in the Milky Way. If even a fraction of their planets are habitable, the universe could be teeming with worlds where life clings on, not in sun-drenched paradises, but in the stubborn shadows of tiny, tempestuous stars. The search for answers begins with our nearest neighbor, a world so close we can almost taste its mysteries. Picture a star so small and cool that it burns red for trillions of years, not the brief, blazing lifetime of stars like our Sun, but a slow, steady glow that could outlast entire galaxies. This is TRAPPIST-1, an ultra-cool dwarf star just 39 light-years away, and its 7 rocky planets form one of the most jaw-dropping planetary systems ever discovered. Each world is roughly Earth-sized, packed so tightly around their star that a year on the innermost planet lasts just 1.5 Earth days, while the outermost still completes its orbit in under 20 days. But here's what makes this cosmic lineup truly extraordinary. 3 of these worlds orbit squarely in the habitable zone, where liquid water could exist on their surfaces. When astronomers first announced the system in 2017, the implications were staggering. Never before had we found so many Earth-sized planets around a single star, let alone with multiple candidates for habitability. The innermost planets, like TRAPPIST-1b and C, are likely scorching hot, tidal-locked worlds with one side permanently facing their dim star. But the middle trio, 1e, 1f, and 1g, sit in that Goldilocks zone where temperatures might allow oceans, lakes, or even atmospheres thick enough to nurture life. Early climate models suggest some could be water worlds entirely covered in global seas, while others might resemble a temperate version of Mars with patchy landmasses peeking through ice. The James Webb Space Telescope has already begun unraveling their secrets. In 2023, JWST trained its infrared eye on TRAPPIST-1b, analyzing the starlight filtering through its atmosphere during transits. While this innermost planet turned out to be a barren rock with no detectable atmosphere, likely stripped away by its star's early fury, the real prizes are the habitable zone siblings. Future observations will hunt for water vapor, carbon dioxide, or even methane in their skies. The presence of these gases could hint at geological activity, oceans, or even biological processes. But TRAPPIST-1 planets come with cosmic hurdles. Their star, though long-lived, is prone to violent flares that could bathe the worlds in radiation. Tidal forces might lock them into eternal day and night sides, creating extreme weather patterns. And without a gas giant like Jupiter to deflect asteroids, their surfaces could be pummeled by impact. Yet life is nothing if not adaptable. Microbial ecosystems might thrive in subsurface oceans or in the twilight bands between scorching days and frozen nights. What makes this system so revolutionary isn't just the number of planets, it's the blueprint it offers. If red dwarfs like TRAPPIST-1, which make up most stars in the galaxy, commonly host rocky worlds in their habitable zones, the universe could be overflowing with real estate for life. These 7 worlds are a test case, a laboratory for understanding how common or rare Earth-like conditions might be, with JWST poised to analyze their atmospheres in unprecedented detail. We're standing on the brink of answers. Are they barren rocks, steamy jungles, or something in between? The data streaming back could redefine our place in the cosmos, one tantalizing world at a time. Far beyond our solar system, a world called K2-18b orbits a dim red star 120 light-years away, and what the James Webb Space Telescope found there sent shockwaves through astronomy. In 2023, JWST infrared gaze pierced the planet's hazy atmosphere, uncovering something revolutionary: unmistakable signatures of water vapor swirling above a surface that might be entirely flooded. This wasn't just another exoplanet detection, it was our first concrete evidence of a Hycean world, a theorized class of planets with hydrogen-rich atmospheres blanketing vast globe-spanning oceans. K2-18b is unlike anything in our solar system. Dubbed a super-Earth, it's about 2.6 times wider and 8 times heavier than our planet, placing it in a bizarre category between rocky worlds like Earth and gas dwarfs like Neptune. But what makes it truly extraordinary is its position in the habitable zone of its star, a sweet spot where temperatures could allow liquid water to pool. JWST spectral analysis didn't just spot water, it also detected traces of carbon dioxide and methane, a chemical cocktail that, on Earth, often signals biological activity. The data paints a picture of a steamy, thick atmosphere hugging an ocean so deep it might lack any land at all, a planetary-scale marine wonderland with conditions unlike anything we've seen before. Hycean planets like this rewrite the rules of habitability. Scientists have long speculated that worlds with hydrogen-rich atmospheres could maintain liquid water even far from their stars, thanks to the greenhouse effect trapping heat. K2-18b's potential ocean isn't like Earth's. It could be hundreds of miles deep with pressures so crushing that water forms exotic hot ice or superfluid layers. Yet, in its upper layers, where temperatures and pressures ease, life might find a way. Earth's own oceans teem with microbes thriving in hydrothermal vents and lightless depths. Could similar extremophiles float in K2-18b's alien seas, metabolizing dissolved gases or organic molecules raining from the sky? Not everyone's convinced, though. Some researchers argue the planet's atmosphere might be too hot and thick, with surface temperatures soaring past the boiling point of water. Others caution that without proof of a solid surface, the ocean might just be a supercritical fluid, a strange, gaseous liquid hybrid state. Even the methane detection raises eyebrows. While it could be a biosignature, it might also come from volcanic activity or photochemical reactions in the atmosphere. The debate is fierce because the stakes are cosmic. If Hycean worlds can host life, the galaxy might be filled with aquatic paradises hiding beneath their misty veils. What comes next is even more thrilling. JWST will revisit K2-18b to hunt for dimethyl sulfide, a molecule that, on Earth, is only produced by living organisms like phytoplankton. Finding it there would be the strongest hint yet of alien biology. Meanwhile, astronomers are compiling a list of other Hycean candidates, planets where distant oceans might ripple under alien suns. K2-18b isn't just a scientific curiosity, it's a beacon pointing toward a new frontier in the search for life. Whether it's a waterlogged Eden or a steamy pressure cooker, one thing's certain: the universe keeps surprising us with places that defy expectations, proving that habitable worlds come in shapes we're only beginning to imagine. In October 2017, astronomers spotted something streaking through our solar system that defied all expectations: a mysterious, cigar-shaped object moving too fast to be bound by the sun's gravity. Named Oumuamua, Hawaiian for scout, it was the first interstellar visitor ever detected passing through our cosmic neighborhood. But what made this fleeting guest truly bizarre wasn't just its origin, it was the way it behaved. Unlike typical comets or asteroids, Oumuamua accelerated slightly as it raced away from the sun, as if pushed by an unseen force. This tiny deviation ignited a firestorm of debate, splitting scientists into two camps: those hunting for natural explanations, and those daring to ask if we just witnessed our first brush with alien technology. The naturalist camp points to exotic but plausible cosmic phenomena. When comets approach the sun, their ices heat up and erupt into space, creating a visible tail that acts like a natural thruster. Oumuamua showed no such tail, but some researchers suggest it might have vented hidden pockets of hydrogen gas trapped beneath its surface, a process that wouldn't leave a visible trail. Others propose it was a chunk of frozen nitrogen sheared off a Pluto-like exoplanet, with sunlight vaporizing its surface to create thrust. These theories paint Oumuamua as a rare but natural interstellar iceberg, shaped by forces we're only beginning to understand. Then there's the electrifying alternative: could Oumuamua have been artificial? Harvard astronomer Avi Loeb famously floated the idea that the object's unusual acceleration and peculiar shape, a flattened, pancake-like form, might hint at a light sail, a spacecraft propelled by the pressure of starlight. Such technology is already being tested on Earth, with projects like Breakthrough Starshot aiming to send tiny, sail-powered probes to nearby stars. If Oumuamua were a relic of an alien civilization, even a derelict one, it would explain the absence of a visible coma. no outgassing because no natural ices, just reflective surfaces catching sunlight. The implications ripple far beyond one strange object. If Oumuamua was natural, its existence suggests our galaxy is teeming with similar interstellar wanderers, some of which could be ferrying the raw ingredients of life between stars. This concept, called panspermia, posits that life's building blocks or even dormant microbes might hitch rides on these cosmic nomads, seeding planets like Earth. But if it was artificial, even partially, the ramifications are staggering. It would mean we're not just searching for life, we might have already intercepted its artifacts drifting silently through the void. What's undeniable is how Oumuamua exposed the limits of our knowledge. By the time we spotted it, the object was already speeding away, leaving us with mere weeks of blurry observations. Future telescopes like the Vera Rubin Observatory will scan the skies for more visitors, ready to capture them earlier and study them in detail. Whether natural or otherwise, Oumuamua was a wake-up call, a reminder that the cosmos is far stranger than we imagine, and that the next interstellar interloper could hold answers to questions we've barely begun to ask. The universe, it seems, is full of scouts. We just need to learn how to read their messages. Some of the universe's most mysterious signals don't come from stars, planets, or even black holes. They're sudden, blazing bursts of radio waves so powerful they outshine entire galaxies for milliseconds before vanishing without a trace. These are fast radio bursts, or FRB, and for years their origins were one of astronomy's greatest puzzles. Then, in 2016, everything changed. Astronomers discovered FRB 121102, the first repeating fast radio burst, a signal that didn't just flash once but fired off multiple pulses in a pattern that defied natural explanations. Suddenly, the question wasn't just what causes these bursts, but what or who could be controlling them. What makes FRB 121102 so extraordinary isn't just its repetition. It's the structure of those repetitions. Unlike random cosmic explosions, this signal cycles through a precise cadence, a 90-day rhythm of activity followed by 67 days of silence. That kind of regularity is almost unheard of in nature. Imagine a lighthouse flashing with mathematical precision across billions of light years, its beam cutting through the void with intentional timing. Even stranger, when scientists analyzed the individual bursts, they found complex patterns in their polarization, a fingerprint suggesting the waves had twisted through powerful magnetic fields, like those near neutron stars or technological megastructures. The leading natural theory points to magnetars, supermagnetic remnants of dead stars, whose crust-quaking starquakes might generate these eruptions. Some researchers suggest the periodicity could stem from the wobble of a magnetar's rotation or debris clumps in its orbit. But others note a haunting possibility: artificial beacons. The idea isn't as far-fetched as it sounds. If an advanced civilization wanted to announce its presence, encoding information in polarized radio waves would be an efficient way to stand out against cosmic noise. The burst's brevity and power match predictions for directed energy propulsion systems. Imagine a light sail's photon drive, so immense it leaks detectable pulses across interstellar space. Even skeptics admit the numbers are eerie. The energy required to produce FRB 121102 signal would demand harnessing the entire output of a sun-like star. Yet the patterns resist Occam's razor. Why would nature craft such meticulous timing without a function? The debate rages because the stakes are cosmic. We're either glimpsing an unprecedented astrophysical phenomenon or brushing against something far more profound. Future telescopes like the Square Kilometre Array aim to pinpoint more repeating FRBs, searching for commonalities that could crack the code. Until then, these enigmatic signals linger at the edge of understanding, whispering a tantalizing question: are we listening to the universe's heartbeat or deciphering its first deliberate message? In the vast cosmic tapestry, some stars don't behave like they should, and none have baffled astronomers more than KIC 8462852, better known as Tabby's star. Nestled in the constellation Cygnus, about 1,400 light-years away, this seemingly ordinary star began making headlines in 2015 when scientists noticed something extraordinary. Its light wasn't just dimming slightly like most stars with orbiting planets. Instead, it was plunging in brightness by up to 22% in chaotic, unpredictable dips, as if something colossal, something unnatural, was passing in front of it. The irregularities were so extreme that researchers couldn't shake one electrifying possibility. Could we be witnessing the shadow of an alien megastructure, a Dyson sphere under construction? The concept of a Dyson sphere comes straight from the pages of science fiction, a hypothetical superstructure built by an advanced civilization to harness the entire energy output of its star. Picture a vast swarm of solar panels or a lattice of orbiting habitats encircling the star, capturing its light and leaving telltale dips in brightness as they move. Tabby's star's bizarre light curve fit this sci-fi scenario eerily well, sparking a frenzy of speculation. But before we jump to conclusions, nature offers alternative explanations. Some scientists argue the star's dimming could stem from massive clouds of dust, possibly from comet swarms or even a shattered planet creating debris. Others suggest internal stellar activity, like gigantic sunspots or magnetic storms, could be to blame. What makes Tabby's star so compelling isn't just its strangeness, it's the company it keeps. Since its discovery, astronomers have identified other Dyson sphere candidates, stars with similarly peculiar dimming patterns. Epoch 204376071, for example, dims by a staggering 80% at irregular intervals, while V1333 Cygni exhibits slow, decade-long fading. Then there's Boyajian's star, another erratic dimmer with fluctuations that defy conventional astrophysics. Each of these cosmic oddballs pushes us to reconsider the line between natural phenomena and potential technosignatures, the fingerprints of intelligent design. The search for answers has led to some of the most creative astronomy in decades. Radio telescopes have scanned Tabby's star for artificial signals, while infrared observations hunt for the waste heat a Dyson sphere would emit. So far, the results are inconclusive, no clear signs of alien engineering, but no perfect natural explanations either. That ambiguity is what keeps the mystery alive. If these stars aren't harboring megastructures, their behavior forces us to confront gaps in our understanding of stellar physics, and if even one of them turns out to be artificial, the implications would redefine humanity's place in the cosmos. This isn't just about finding aliens, it's about testing the limits of our imagination. The universe has already shown us planets that rain glass and moons with underground oceans. Why not civilizations capable of engineering stars? Whether Tabby's star is a cosmic construction site or a natural puzzle we've yet to solve, it reminds us that the universe is stranger than we can suppose. And as our telescopes grow sharper, we might just find that the line between science fiction and science fact is thinner than we ever dared to dream. While we scan the cosmos for natural signs of life, scientists are also hunting for something far more deliberate: clues that advanced civilizations might be broadcasting their presence across the galaxy. These markers, called technosignatures, range from artificial radio transmissions to atmospheric pollution, and they're turning our telescopes into cosmic eavesdropping devices. The James Webb Space Telescope has already revolutionized this search, not just by spotting exoplanets but by dissecting their atmospheres for signs of technology. Imagine detecting chlorofluorocarbons, the same chemicals that once ate away at Earth's ozone layer, floating in the skies of a distant world. That wouldn't just hint at life, it would scream industrial civilization. The search for alien radio signals, pioneered by projects like SETI, has evolved dramatically. Instead of just listening for deliberate broadcasts, astronomers now hunt for accidental leaks, the cosmic equivalent of picking up stray Wi-Fi signals from a neighboring planet. Some telescopes, like the Allen Telescope Array, scan thousands of stars simultaneously, filtering through radio noise for patterns that betray artificial origins. Then there's the laser angle. Powerful optical telescopes scan for nanosecond flashes of light that could be interstellar beacons or even spacecraft propulsion systems. In 2021, the Breakthrough Listen project detected a mysterious laser-like signal from Proxima Centauri's direction, sparking fevered debate before it was eventually attributed to human interference. But the near miss proved our techniques are sharp enough to catch such fleeting signs. JWST takes the hunt to a new level by analyzing the chemical fingerprints of exoplanet atmospheres. While biosignatures like oxygen or methane suggest life, technosignatures like nitrogen dioxide or sulfur hexafluoride, byproducts of advanced industry, would imply intelligence. The telescope's infrared gaze can even spot artificial light sources. A planet with night-side illumination far brighter than its stars' reflected light might suggest sprawling cities or massive orbital mirrors. One hypothetical scenario involves detecting Fermi bubbles, vast structures harnessing a star's energy, visible as unusual infrared excesses around certain stellar systems. We haven't found any yet, but the very possibility reshapes how we imagine civilizations far older and more advanced than our own. Critics argue that technosignature searches are speculative, like fishing for needles in a galaxy-sized haystack. After all, an alien civilization might communicate via neutrino beams or quantum entanglement, methods invisible to our current tools. Others note that advanced societies could transition to clean energy, leaving no industrial traces in their atmospheres. But proponents counter that even a single unambiguous detection, say, a repeating radio signal matching no known natural phenomenon or a planet shimmering with artificial lights, would redefine humanity's place in the cosmos. The paradox is striking. We're using our own technological adolescence as a blueprint to find civilizations that may have outgrown such markers entirely. Yet the search continues, because if we don't look, we'll never know who or what might be signaling back. The universe might not just host life, it could be actively spreading it. Imagine a scenario where life's building blocks hitchhike across the cosmos, riding the backs of asteroids and comets to see distant worlds. This idea, called panspermia, isn't just science fiction, it's a theory with tangible evidence, and some of the most compelling clues come from ancient meteorites that landed right here on Earth. Take the Murchison meteorite, a charred space rock that fell in Australia in 1969. When scientists cracked it open, they found something astonishing: over 90 different amino acids, the organic molecules that form the basis of proteins and life itself. Even more mind-blowing, nearly half of these amino acids don't exist naturally on Earth, proving they formed somewhere out in the void of space. What makes Murchison so revolutionary isn't just the presence of these molecules, it's their complexity. Some of the amino acids were arranged in ways that mirrored the structures found in earthly proteins, suggesting the universe has a knack for assembling life's ingredients even in the harshest environments. Even more intriguing, the meteorite contained nucleobases, the critical components of DNA and RNA. These discoveries paint a picture of a cosmos teeming with probiotic chemistry, where the raw materials for life are forged in interstellar clouds and delivered to planets via cosmic FedEx. If simple molecules like these can survive the brutal journey through space, could more complex organisms like bacteria or even dormant spores also make the trip? That's where things get controversial. In 1996, scientists examining LH84001, a Martian meteorite discovered in Antarctica, made a bombshell announcement. They'd spotted microscopic structures resembling fossilized bacteria. The tiny, worm-like shapes embedded in the rock looked eerily similar to earthly microbes, complete with what some researchers argued were mineral byproducts consistent with bacterial metabolism. The media erupted with headlines declaring we'd found proof of ancient Martian life, but skepticism followed just as quickly. Critics pointed out that non-biological processes like mineral crystallization or contamination from Antarctic ice could create similar shapes. Even the famed nanobacteria spotted in the meteorite were later shown to be far smaller than any known life form, raising doubts about whether they could function as living cells at all. The debate over LH84001 highlights the razor-thin line between groundbreaking discovery and scientific false alarm. Yet, even if the Martian meteorite doesn't prove extraterrestrial life, it does something equally profound. It forces us to refine our tools and expectations. Modern techniques like high-resolution 3D imaging and isotopic analysis are now being applied to these space rocks, searching for patterns that unmistakably betray biology. Meanwhile, new meteorite finds like the one that crashed into Sudan's Nubian desert in 2008, laden with probiotic organics, continue to bolster the case that the cosmos is a delivery service for life's raw materials. Panspermia remains a tantalizing what-if. If amino acids and nucleobases rain down on planets across the galaxy, does that mean life elsewhere might share a common cosmic ancestry with us? Could Earth itself have been seeded by a meteorite like Murchison, jump-starting biology before evolution took the wheel? The answers might lie in future sample return missions or in deeper analysis of meteorites still waiting to be cracked open. One thing's certain, the universe isn't just a passive backdrop for life. It's an active participant shuttling the ingredients across the void, daring us to piece together how far the chain of life truly stretches. Rising from the heart of the Milky Way like twin cosmic balloons, the Fermi bubbles stretch 25,000 light-years above and below our galaxy's plane, a colossal hourglass of high-energy radiation glowing in gamma and X-rays. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these gargantuan structures remain one of the most puzzling features in our galactic backyard. Their energy output defies easy explanation, emitting particles moving at nearly the speed of light. Conventional astrophysics suggests they're remnants of an ancient supermassive black hole eruption, a belch from Sagittarius A, our galaxy's central black hole that occurred millions of years ago. But what if there's another, far more speculative possibility lurking in those shimmering lobes? Could these bubbles be the fading echo of a long-vanished civilization's ultimate power project? The idea isn't as wild as it seems. The bubble's symmetry and sheer scale, each lobe large enough to swallow 10,000 solar systems, mirror theoretical designs for Dyson spheres, but on a galactic level. Imagine a Type 3 civilization, advanced enough to harness not just a star's energy, but the output of an entire galaxy. Such a society might construct energy capturing megastructures around the central black hole, converting its monstrous appetite into usable power. Over millennia, the waste heat from these hypothetical constructs could inflate vast bubbles of radiation, expanding outward until they resembled the Fermi structures we see today. Even more tantalizingly, recent observations reveal substructures within the bubble's filaments and caps of intense emission that don't neatly fit standard astrophysical models. These could be the skeletal remains of engineered frameworks, their purpose lost to cosmic time. Yet nature has its own bag of tricks. Alternative theories propose the bubbles resulted from a frenzy of star formation near the galactic center, with countless supernovae pumping energy into interstellar space. Others suggest periodic accretion events when Sagittarius A voraciously consumes a passing star or gas cloud could create such outbursts. The bubble's sharp edges, though, remain a sticking point. Natural phenomena tend to diffuse over time, but these boundaries are remarkably crisp, as if contained by some unseen force. Could magnetic fields be shaping them, or does their precision hint at something more deliberate? The hunt for answers is accelerating. New instruments like the imaging X-ray polarimetry explorer are analyzing the bubble's polarization, hunting for clues in how their light twists. Meanwhile, radio telescopes scour the structures for unusual synchrotron radiation patterns that might betray artificial origins. Even if the explanation turns out to be purely natural, the Fermi bubbles remind us that our galaxy still holds epic mystery structures so vast we once overlooked them entirely. Whether they're the gravestones of a galactic empire or simply the universe showing off its raw power, one thing's certain: the cosmos keeps its most astonishing secrets hiding in plain sight. On a quiet August night in 1977, an astronomer working with Ohio State University's Big Ear radio telescope jotted down 3 letters that would ignite decades of speculation. Wow. The signal he just detected wasn't just unusual, it was unlike anything ever recorded. For 72 electrifying seconds, a narrowband radio transmission blasted from the constellation Sagittarius at precisely the frequency hydrogen resonates in deep space, 1420 MHz. This wasn't random cosmic noise. It was a signal so perfectly engineered for interstellar communication that even the most skeptical scientists couldn't dismiss it outright. Then, just as suddenly as it appeared, it vanished, never to return despite 40 years of relentless searching. The WOW signal remains astronomy's most tantalizing ghost, a whisper from the cosmos that refuses to be explained. Modern analysis has only deepened the mystery. When researchers revisited the data with 21st-century techniques, they confirmed the signal's artificial-seeming structure. It wasn't just narrow but bandwidth-locked, meaning it occupied less than 10 kHz of space on the radio spectrum. Natural cosmic phenomena like pulsars or quasar emissions don't behave this way. They scatter across frequencies. The WOW signal, by contrast, was surgically precise, as if someone had tuned a cosmic transmitter to the clearest possible channel for shouting across the galaxy. Even its intensity followed a distinct bell curve, spiking and fading in a pattern consistent with a distant source sweeping past Earth due to our planet's rotation. But here's the kicker: no known human-made satellite or aircraft matched its profile, and subsequent searches found zero interference at that frequency before or since. Theories abound, but none fit perfectly. Could it have been a reflected signal from Earth bouncing off space debris? Unlikely. The required alignment would have been a 1 in a million fluke. A comet's hydrogen cloud, a passing object in our solar system emitting radio waves, both were proposed, but follow-up observations disproved them. The most electrifying possibility lingers. Was this an intercepted alien transmission? A brief blip from a civilization briefly pointing their beacon in our direction? The signal's brevity plays into this idea. If extraterrestrials were methodically scanning the galaxy with targeted pulses, we might only catch a fleeting glimpse as their beams swept over us. Today, the hunt for WOW-like signals has gone interstellar. Projects like Breakthrough Listen now deploy AI to sift through millions of radio frequencies simultaneously, searching for that elusive needle in the cosmic haystack. New telescopes like the Allen Telescope Array can monitor multiple star systems at once, while machine learning algorithms filter out earthly interference with unprecedented precision. There's even a push to explore optical SETI, scanning for laser pulses that might outshine radio as the communication method of advanced civilizations. Yet despite these leaps in technology, the WOW signal stands alone, a singular enigma that refuses to repeat. What makes this decades-old mystery so enduring isn't just the unanswered questions, it's what it reveals about our search for cosmic company. The WOW signal taught us that the universe can surprise us in ways we're barely equipped to recognize. It forced astronomers to confront the unsettling truth that even our best efforts might catch only fragments of a conversation happening light years away. Whether it was a cosmic coincidence, an unidentified natural phenomenon, or the first faint echo of another intelligence, one thing's certain: somewhere out there, the universe is still whispering. We just have to learn how to listen. Imagine a planet where oceans don't lap against sandy shores, they boil, where mountains aren't made of stone but of molten rock, and where the very air might be laced with vaporized metal. This isn't a nightmare vision of hell. It's K2141b, a real exoplanet discovered in 2018 that defies every notion of what makes a world habitable. Tidally locked to its star, this scorching orb has a dayside hot enough to vaporize rock temperatures soaring above 5,000 degrees Fahrenheit, while its nightside plunges into frigid darkness. Yet nestled between these extremes lies a sliver of possibility, the Terminator line, where perpetual twilight might just harbor conditions ripe for life. The Terminator zone of a tidally locked planet is like a cosmic balancing act. On K2141b, this narrow band experiences neither the star's relentless fury nor the deep freeze of eternal night. Instead, temperatures here could hover in a range where certain molecules, even water, might exist in liquid form, if only briefly. But how could life survive on a world where the ground itself is molten? The answer lies in Earth's own extremophiles. Microbes like Metallosphera sedula thrive in volcanic vents, metabolizing sulfur and iron in conditions that would kill most organisms. On K2141b, similar life forms might cling to rocky outcroppings near the Terminator, where geothermal heat meets just enough cooling to prevent annihilation. What's even more astonishing is the planet's atmosphere, or what's left of it. K2141b's dayside is so hot that rock evaporates into a thin, mineral-laden haze which powerful winds carry toward the night side. There, these vapors condense into pebbles and rain back down in a relentless cycle. This dystopian weather might seem inhospitable, but it could also create a chemical conveyor belt. Minerals transported from the dayside to the Terminator might provide raw materials for exotic metabolisms, while the constant recycling of material could sustain a delicate equilibrium. Picture microbes existing like desert nomads, migrating with the shifting winds to stay within the narrow band where conditions are bearable. The idea of life on a lava planet forces us to rethink the very definition of habitability. Earth-like conditions may not be the only pathway for biology. On K2141b, organisms might rely on silicon-based chemistry instead of carbon, or draw energy from thermal gradients rather than sunlight. Some theories even suggest that the planet's mineral-rich rain could form temporary pools in the Terminator zone, offering fleeting oases for life to emerge. It's a harsh existence, but life has a knack for exploiting even the tiniest cracks in the universe's armor. Future telescopes like the James Webb Space Telescope could soon turn speculation into science. By analyzing the Terminator zone's atmospheric composition, scientists might detect biosignatures, gases like methane or sulfur dioxide that don't belong in abiotic conditions. Even more telling would be the presence of chemical disequilibrium, where compounds coexist in ratios that only life could maintain. Until then, K2141b stands as a testament to nature's creativity, proving that life's potential isn't limited to Earth-like havens. Sometimes it's in the most unforgiving corners of the cosmos that the rules of biology get rewritten. Drifting through the eternal night of interstellar space, untethered from any star, rogue planets are cosmic nomads, dark, frozen worlds exiled from their birth systems by gravitational chaos. But what if some of these wandering outcasts carry secrets beneath their icy shells? Scientists now believe certain rogue planets might conceal vast subsurface oceans, warmed not by starlight but by the slow radioactive heartbeat of their own cores. Picture an Earth-sized ice ball adrift in the void, its surface temperature near absolute zero, yet beneath miles of frozen crust, tidal forces and decaying isotopes could maintain liquid water for billions of years. These aren't just barren wastelands, they're potential arcs for extremophile life, carrying the flame of biology through the galaxy's coldest deserts. The physics at play is staggering. Without a star's warmth, rogue planets rely on internal heat, either from leftover formation energy or radioactive elements like uranium and thorium simmering in their cores. Some models suggest thicker ice layers could act as insulating blankets, trapping geothermal heat like a cosmic thermos. Add tidal flexing from a large moon if the planet retained one during ejection, and you have friction-generated warmth churning the depths. The combination creates stable environments where liquid water might persist, similar to subglacial lakes in Antarctica or the buried ocean of Europa. But here's the twist: rogue planets could outnumber stars in the Milky Way by a factor of 20. If even a fraction shelter hidden seas, the galaxy might be awash in these drifting oases. Life in such isolation would face extraordinary challenges, but Earth's own extremophiles prove how adaptable biology can be. Microbes like Desulphirudes audax theater thrive miles underground in South African mines, subsisting solely on radiation breakdown products from surrounding rock. No sunlight, no oxygen, no problem. A rogue planet's ocean, rich in minerals from hydrothermal vents or dissolved organics from its icy ceiling, could host similar ecosystems. Chemosynthesis might replace photosynthesis, with organisms metabolizing hydrogen or sulfur compounds. Some theorists even speculate about multicellular life in these abysses. Creatures evolved to endure crushing pressure and eternal darkness, their existence unbounded by day-night cycles or seasons. The most tantalizing rogue planets might be those ejected during their system's chaotic infancy, when they were still young and geologically vibrant. Imagine a world like early Earth, rich in volatiles and radioactive elements catapulted into the void before life could arise on its surface. Its subsurface ocean, shielded from cosmic radiation by kilometers of ice, could become a sanctuary where life emerges independently of starlight. Unlike tidal-locked exoplanets or scorching lava worlds, rogue planets offer something unique: stability. No solar flares to strip atmospheres, no gravitational turbulence, just quiet, relentless darkness punctuated by geothermal whispers. Detecting these loners isn't easy, but astronomers have tricks. Gravitational microlensing, where a rogue planet briefly bends light from a background star, has already revealed candidates. Future telescopes like the Nancy Grace Roman Space Telescope could spot hundreds more, while infrared surveys might catch the faint thermal glow of young rogues still warm from formation. The real breakthrough would come if we could sample plume material from an icy rogue's cryoval. Cano's a long shot, but missions like Europa Clipper prove we're developing the tools to explore subsurface oceans remotely. Rogue planets shatter the paradigm that life requires a star. If biology can flourish in these nomadic worlds, the galaxy's habitable real estate expands exponentially, not just around stars but in the infinite abyss between them. They're reminders that life, once ignited, is tenacious. It doesn't need sunlit shores or balmy breezes. Sometimes all it needs is a dark corner, a bit of heat and time. The universe might be teeming with such wanderers, each carrying the potential for life in its silent, frozen heart. White dwarfs should be pristine cosmic embers cooling quietly after their stellar lives end, their atmospheres composed almost entirely of hydrogen and helium. But something bizarre keeps showing up in their light spectrum: metals. Not just trace amounts, but heavy elements like iron, calcium, and even gold elements that have no business floating in the atmospheres of these dead stars. The mystery deepened when astronomers realized these metals weren't remnants from the white dwarf's violent past. They were fresh, as if the star had recently ingested something rocky. The chilling conclusion: these ancient stellar corpses might be the graveyards of obliterated planets, worlds that could have once been lush, watery, and even habitable. The process is as violent as it is poetic. When a star like our Sun exhausts its nuclear fuel, it swells into a red giant, engulfing inner planets like Mercury and Venus. Earth might barely escape, scorched but intact, until the star collapses into a white dwarf. its gravitational pull now so intense that surviving planets are yanked into unstable orbits. Over time, they stray too close, and the white dwarf's tidal forces shred them into rubble. Imagine an entire planet torn apart in slow motion, its crust and mantle ground into dust that rains down onto the dead star's surface. The heavier elements sink, while lighter metals like sodium and potassium linger in the atmosphere, detectable from light years away. It's forensic astronomy, the spectral fingerprints of planetary murder. But here's the twist that makes this discovery hauntingly relevant to the search for life. Some of these devoured worlds might have been Earth-like. In 2023, researchers analyzing the white dwarf G238 found traces of lithium, potassium, and water. Ingredients that, when combined in the right ratios, point to planets with continental crusts and oceans. Another white dwarf, 200 light-years away, showed signs of a planet with an iron core and silicate mantle, eerily similar to Earth's composition. The implications are staggering. If rocky, water-rich planets were common enough to end up as white dwarf meals, how many of them once hosted conditions ripe for life? The metals aren't just tombstones, they're time capsules. By studying their ratios, scientists can reconstruct the geology of long-dead worlds. One white dwarf's atmosphere revealed a planet richer in water than Earth, while another's debris disk hinted at a world with more graphite than diamond, suggesting carbon-rich terrains unlike anything in our solar system. These aren't just abstract data points, they're glimpses of real landscapes that existed for billions of years before meeting their fiery end. If life arose on any of them, its remnants might still be floating in that debris, frozen in the spectral lines we observe today. Yet the most profound lesson lies in the timing. White dwarfs can retain these metals in their atmospheres for only a few million years before gravity drags them beneath the surface. That means the planetary destruction we're witnessing is recent by cosmic standards. The universe isn't just showing us ancient relics, it's offering snapshots of apocalypses unfolding in real time. And if planets are still being shredded today, it means the ingredients for life, water, organics, protective atmospheres, were present right up until the end. The cosmos doesn't just build habitable worlds, it destroys them too, leaving behind stellar gravestones that whisper stories of lost oceans, vanished continents, and perhaps, just perhaps, civilizations that burned bright before the dark. What if we're not alone in the universe but being deliberately ignored? This unsettling possibility lies at the heart of the zoo hypothesis, a theory suggesting advanced civilizations might be observing us like animals in a cosmic wildlife preserve, choosing not to interfere. First proposed in the 1970s by MIT astronomer John Ball, the idea has gained new traction thanks to sophisticated simulations and ethical debates about humanity's own future behavior toward less developed species. Recent computer models have explored how a single, galactic curator civilization could enforce a no-contact policy across vast interstellar distances. These simulations reveal eerie parallels to Earth's own uncontacted tribes cultures like the Sentinel Islanders, shielded from outside interaction by international law. In the cosmic version, humanity might be quarantined not by geography but by technology. Advanced societies could be monitoring our progress silently, waiting for us to reach some threshold, whether technological maturity, political stability, or even moral enlightenment, before initiating first contact. The stunning part, we wouldn't necessarily know. Any civilization capable of such restraint would also possess the means to remain utterly invisible to our primitive detection methods. Ethical arguments add another layer to this hypothesis. If humanity discovered a planet with a burgeoning intelligent species, how would we act? Historical precedent isn't encouraging colonialism, and cultural contamination loom large as cautionary tales. Some astrobiologists argue that non-interference might be a universal ethical standard among advanced civilizations, a galactic prime directive akin to Star Trek's fictional protocols. Others counter that diversity in alien motivations would make uniformity unlikely. What if some civilizations choose contact while others abstain? The result could be a patchwork of observed and interactive zones across the galaxy, with Earth strategically placed in a quiet corner. The Fermi paradox, the glaring absence of extraterrestrial visitors despite the universe's apparent readiness for life, finds uneasy resolution in this theory. Rather than a silent cosmos, we might inhabit a carefully managed one, with our planet designated as a controlled experiment or cultural sanctuary. Even our searches for alien signals could be deliberately thwarted, like a zookeeper hiding behind one-way glass while animals peer vainly at their reflections. Yet the zoo hypothesis isn't without flaws. It assumes a level of coordination and altruism that may not exist among alien societies. Competition for resources, ideological differences, or simple curiosity might override any non-interference pact. And if we are being observed, why no trace, no probes, no atmospheric anomalies? Some researchers propose modified versions, the wilderness hypothesis, where civilizations avoid contact simply because space is vast and interaction isn't worth the effort, or the planetary park model, where Earth is preserved not for study, but for its rarity as a living world. The chilling beauty of this idea lies in its unfalsifiability for now. As our telescopes grow sharper and our AI detectors more nuanced, we might uncover subtle evidence of cosmic curation, unexplained absences of nearby technosignatures, or patterns in exoplanet data that suggest artificial selection. Until then, the zoo hypothesis stands as both a sobering critique of human exceptionalism and a humbling reminder that the silence around us may not be empty, just intentional. Whether it's true or not, the theory forces us to confront an uncomfortable question. If the universe is watching, are we ready to be seen? What if the universe's most abundant substance isn't just an invisible scaffold holding galaxies together, but a hidden stage for life itself? Dark matter makes up 85% of the cosmos mass, yet we've never seen it directly. It doesn't absorb, reflect, or emit light. It barely interacts with the ordinary matter we're made of. But here's the radical idea some scientists dare to propose. What if dark matter isn't just a cosmic placeholder? What if it's teeming with its own form of biology, so alien we lack the tools to recognize it? The concept sounds like science fiction, but the math offers tantalizing possibilities. If dark matter particles, whatever they are, can interact weakly with each other, they might form complex structures beyond our comprehension. Imagine self-replicating dark matter molecules, or even dark matter cells that metabolize hypothetical dark energy. These entities wouldn't just be invisible, they'd exist in a parallel reality overlapping our own, oblivious to stars, planets, or light. Some theorists speculate that dark matter life might congregate in halos around galaxies, drawn to gravitational wells like microbes swarming a nutrient source. Others suggest it could resemble vast, diffuse intelligences operating on timescales so slow, a single thought might span millennia. Detecting such life would require redefining biology itself. Our current search for extraterrestrials focuses on water, carbon, and DNA, but dark matter organisms might use none of these. Instead of chemical bonds, they could rely on gravitational or weak nuclear interactions. Their version of reproduction might involve quantum entanglement or the spontaneous emergence of new particles. Even their perception of reality would differ. Where we see a starry sky, they might navigate by ripples in the fabric of spacetime itself. The most compelling argument for dark matter life comes from sheer probability. If ordinary matter, a cosmic afterthought, can give rise to consciousness, why not the dominant form of mass in the universe? Of course, skeptics counter that without observable interactions, such life is untestable speculation, but breakthroughs could be closer than we think. Experiments like the Action Dark Matter experiment are hunting for faint whispers of dark matter particles. If they find evidence of even basic dark matter interactions, the door cracks open for more exotic possibilities. Perhaps the most humbling thought is this: dark matter life might already be studying us. To them, our bustling world of light and matter could seem as ghostly and ephemeral as their existence appears to us. The universe's greatest irony might not be that we're alone, but that we're surrounded by neighbors we're fundamentally blind to, living in realms where the rules of life are written in forces we've yet to name. Binary star systems were once thought to be cosmic dead zones for planets. The gravitational tug of war between two stars would shred any fledgling world before it could form. But nature loves proving us wrong. Take Kepler-16b, a Saturn-sized planet 7,000 light-years away that shouldn't exist, nestled snugly between two stars, one about 2/3 the mass of our Sun, the other just a fifth. This gas giant orbits its twin suns every 229 days, tracing a path so stable its skies feature double sunsets straight out of science fiction. The discovery in 2011 shattered old assumptions, revealing that planets don't just survive in binary systems. They can thrive there, with some even finding themselves in habitable zones with Earth-like conditions. What makes these circumbinary planets so fascinating isn't just their resilience, it's the strange new rules of habitability they force us to consider. In Kepler-16b's case, the planet itself is too gaseous for life as we know it, but its existence proves binary systems can host stable orbits. Later discoveries like Kepler-453b, a rocky world in its system's habitable zone, pushed the envelope further. Here, a planet receives 87% the sunlight Earth does, but with a catch. Because its twin stars orbit each other closely, daylight cycles would be chaotic. Some days would last forever as both suns hover overhead, while others might feature staggered sunrises or eerie moments when the smaller star eclipses its larger sibling. Plants evolving under these conditions could develop photosynthesis tuned to different light wavelengths, while animals might adapt to irregular sleep cycles. The real surprise: binary systems might actually enhance life's chances. Two stars mean more consistent energy output. If one star dims, the other could compensate, preventing total freezing. Their combined gravitational influence might also shepherd asteroids into safer orbits, reducing extinction-level impacts. Some models even suggest binary stars could extend habitable zones outward, creating stable regions where single-star systems would be too cold. Take LTT 14045, a pair of red dwarfs hosting a potentially habitable super-Earth. Despite being cooler than our Sun, their combined warmth might render their planets more temperate than expected. Yet challenges abound. Twin stars create complex radiation environments, with solar flares from one potentially stripping atmospheres unless the planet has a robust magnetic field. Tidal forces could also lock planets into eccentric orbits, creating extreme seasons. But life, as we've seen on Earth, is remarkably adaptable. Microbial extremophiles might flourish in the subsurface, while hardier organisms could evolve shielding against radiation. There's even speculation about binary systems hosting Trojan planets, worlds sharing orbits at gravitational sweet spots, leading to shared climates or even shared biospheres if panspermia occurs between them. The implications are cosmic. Binary stars make up over 50% of all Sun-like stars in the Milky Way. If even a fraction host habitable worlds, the galaxy's real estate for life just doubled. Future telescopes like the Habitable Worlds Observatory will scan these systems for biosignatures, hunting for oxygen or methane in their atmospheres. Every new discovery peels back another layer of the universe's creativity, proving yet again that life, if it exists out there, isn't just surviving, it's rewriting the rules of where we should even think to look. Our galaxy isn't just a random scattering of stars, it's a cosmic ecosystem with neighborhoods more hospitable to life than others. Picture the Milky Way divided into distinct zones like a metropolis, where certain regions offer the perfect blend of safety and resources while others are downright hazardous. At the heart of this galactic real estate hunt lies the concept of the galactic habitable zone, a Goldilocks band where conditions are just right for complex life to take root. Too close to the bustling core, and deadly gamma-ray bursts or supernova explosions would sterilize budding civilizations. Too far out in the sparse suburbs, and there wouldn't be enough heavy elements like iron or silicon to form rocky planets in the first place. Astronomers have mapped these life-friendly regions by analyzing three critical factors. First, metallicity, the abundance of elements heavier than hydrogen and helium. These building blocks are forged in stellar furnaces and scattered by supernova, creating a gradient where inner galactic regions are richer in metals. Second, radiation levels. The Milky Way's core is a maelstrom of lethal X-rays and cosmic rays, while the outer edges are quieter but lack the materials for Earth-like worlds. Finally, star density plays a role. Crowded areas mean more frequent close encounters, which could destabilize planetary orbits over billions of years. The sweet spot, a ring about 25,000 light-years from the center, where our own solar system happens to reside. But location isn't everything, timing matters too. Early in the galaxy's history, catastrophic explosions were far more common. Only after enough generations of stars lived and died, seeding space with metals, could life-friendly conditions emerge. Simulations suggest the Milky Way's habitable zone began forming around 8 billion years ago and will remain stable for billions more, offering a generous window for civilizations to arise. There's even evidence that this zone migrates outward over time, like a slow wave of habitability rolling across the galaxy. What's startling is how narrow the ideal conditions might be. Some studies suggest only 10% of the Milky Way stars lie in regions with the right mix of low radiation and adequate metallicity. Even within this band, local hazards exist. Stars passing through spiral arms where supernovae are more frequent could face periodic extinction-level events. Yet life, if it's as tenacious as Earth's extremophiles suggest, might find ways to endure, perhaps retreating underground during cosmic catastrophes or evolving radiation-resistant biochemistry. The implications are profound. If we're searching for alien civilizations, targeting stars in this Goldilocks ring could dramatically improve our odds. Future telescopes like the European Extremely Large Telescope could analyze planetary atmospheres in these regions for biosignatures, while surveys like Gaia precisely map stellar metallicity. There's also a humbling possibility. What if Earth's location isn't just fortunate but necessary? Complex life might require not just a habitable planet, but a habitable neighborhood in the grand galactic city. As we peer deeper into the cosmos, we're not just mapping stars, we're drawing the blueprint for life's cosmic address. We tend to think of quantum mechanics as the domain of supercooled laboratories and particle colliders, a strange, counterintuitive realm that operates on scales far removed from our everyday experience. But what if nature has been harnessing quantum trickery for billions of years? Here on Earth, scientists are uncovering how life itself exploits these bizarre phenomena in ways we're only beginning to understand. Photosynthesis, the very foundation of most ecosystems, relies on quantum coherence, where particles exist in multiple states simultaneously. In plant cells, photons of sunlight get processed with near-perfect efficiency because quantum effects allow energy to explore all possible pathways through chlorophyll molecules at once, choosing the most optimal route. It's as if plants have mastered quantum computing without circuits or code. This revelation flings open a door to astrobiology we never knew existed. If Earth's organisms tap into quantum physics for survival, why wouldn't extraterrestrial life do the same, perhaps in far more advanced ways? Imagine a planet where organisms don't just exploit quantum coherence occasionally, but build entire biological architectures around it. On a world with dim starlight, creatures might evolve photosynthetic systems where energy transfer operates with 100% efficiency through sustained quantum entanglement. Their cells could function like superconductors with electron pathways never losing energy to heat. Some theorists speculate about quantum tunneling enzymes, proteins that help biochemical reactions occur impossibly fast by allowing particles to bypass classical energy barriers entirely. The possibilities grow stranger when considering sensory systems. Earth's migratory birds navigate using quantum-entangled electrons in cryptochrome proteins, allowing them to literally perceive Earth's magnetic field as a visual overlay. On an exoplanet with extreme magnetic fields or tidal locking, life might develop quantum-enhanced sensors that make our magnetoception seem primitive. Picture organisms that see gravitational waves or detect the spin states of distant particles, their biology so finely tuned to quantum vibrations that they experience reality on a fundamentally different level than we do. Even consciousness itself could arise from quantum processes. A controversial idea called orchestrated objective reduction, which suggests microtubules in brain cells might harness quantum states to produce awareness. If true, alien minds could operate via entirely different quantum architectures. Critics argue that quantum effects in biology are too fragile to survive the warm, wet chaos of living cells, a phenomenon known as decoherence. Yet extremophiles keep shattering our assumptions. The discovery of quantum vibronic effects in deep-sea bacteria proves coherence can persist even under high pressure and temperature. This suggests alien life might not only survive harsh environments but thrive by turning quantum fragility into a tool. Ammonia-based organisms on icy moons could use quantum tunneling to drive metabolisms at cryogenic temperatures where classical chemistry would grind to a halt. Sulfur breathers in Venusian clouds might rely on electron spin states to catalyze reactions in acidic environments. The most profound implication: quantum biology could make life detectable across interstellar distances. Traditional biosignatures like oxygen or methane might be supplemented by quantum signatures, specific light polarizations indicating coherent energy transport, or anomalous absorption spectra betraying non-classical photosynthesis. Future telescopes equipped with quantum-optimized sensors could scan exoplanet atmospheres for these telltale fingerprints. We might even discover planets where visible light is scarce, but life flourishes by harvesting energy from quantum vacuum fluctuations or dark matter interactions, processes that would leave entirely novel spectral marks. What makes this frontier so electrifying is its dual nature. We're both uncovering Earth's hidden quantum machinery and using it as a blueprint to imagine life stranger than fiction. The universe likely doesn't limit quantum tricks to carbon-based, water-dependent biology. From silicon organisms exploiting superposition to plasma-based life forms riding quantum waves in stellar atmospheres, the rules are being rewritten. As we peer deeper into the quantum underworld of earthly life, we're not just studying cells, we're decrypting a galactic playbook for how reality itself can be hacked into vitality. For decades, the rare Earth hypothesis has dominated discussions about life's cosmic scarcity, arguing that planets like ours with just the right blend of plate tectonics, a large stabilizing moon, and a perfectly positioned star are vanishingly rare. But a flood of discoveries over the past decade is turning this pessimistic view on its head. The universe, it seems, is far more inventive than we ever imagined. Take exoplanet data first. When astronomers began cataloging worlds beyond our solar system, many expected to find systems resembling ours, orderly, widely spaced planets in neat circular orbits. Instead, the cosmos delivered chaos, planets crammed shoulder to shoulder around red dwarfs, gas giants orbiting their stars backward, super-Earths dancing in fragile resonance chains. At first glance, this disorder appeared to support the rare Earth argument until researchers noticed something startling. Even in these extreme environments, habitable conditions emerge in ways we hadn't anticipated. Tidal heating warms frozen moons into ocean worlds. Thick hydrogen atmospheres insulate rocky planets from stellar flares. Eccentric orbits create part-time, habitable zones where life could survive in seasonal pulses. Then there's Earth's own extremophiles rewriting the rulebook for survival. The discovery of microbes thriving in nuclear reactor waste inside Antarctic icebergs, and even in the crushing depths of the Mariana Trench, proves life isn't just adaptable, it's borderline indestructible. On a planet like Jupiter's moon, Europa, where radiation levels would sterilize Earth's surface, organisms could flourish safely beneath miles of ice. Venus' hellish atmosphere, certain sulfur-breathing bacteria on Earth already thrive in similar acidity and heat. The lesson is clear: life doesn't need Earth-like perfection, just a sliver of opportunity. Even seemingly deadly environments have loopholes biology can exploit. The moon argument, once a cornerstone of the rare Earth hypothesis, has also crumbled under scrutiny. While Earth's large moon stabilizes our axial tilt, preventing extreme climate swings, new simulations reveal alternatives. A thicker atmosphere can dampen tilt variations without lunar help. Binary star systems might provide gravitational balancing acts. Some exoplanets could even stabilize themselves through rapid rotation or interactions with neighboring planets. The galaxy is a laboratory of stability solutions, many of which we're only beginning to model. Perhaps the most compelling rebuttal comes from sheer statistics. With over 5,000 exoplanets confirmed and billions more waiting to be discovered, the law of large numbers kicks in. Even if only 1 in a million stars hosts a planet with the right conditions, the Milky Way alone could still harbor hundreds of thousands of life-friendly worlds. And that's before considering radically different biochemistries: silicon-based life in methane lakes, plasma organisms in stellar atmospheres, or quantum-entangled ecosystems in rogue planets. The universe isn't just capable of creating Earth twins. It's a master of improvisation, crafting life from whatever materials are at hand. This doesn't mean intelligent life is guaranteed everywhere. The leap from microbes to civilizations may still face formidable filters, but the rare Earth hypothesis, while valuable for grounding early exobiology, now feels like a relic of a time when we underestimated both nature's creativity and life's tenacity. As telescopes like JWST peer deeper into exoplanet atmospheres and extremophiles continue to astonish us back home, one truth becomes undeniable: the cosmos isn't just habitable. It's buzzing with possibilities we've only begun to imagine. For nearly 6 decades, the search for extraterrestrial intelligence has combed the cosmos for radio signals, sifting through cosmic noise like detectives scanning a crowded frequency band for whispers of a conversation. But in the age of artificial intelligence, SETI methods are undergoing a revolution, one that's transforming the hunt from a painstaking manual scan to something resembling a celestial intelligence operation. Breakthrough Listen, the most ambitious SETI project ever launched, now deploys machine learning algorithms capable of analyzing millions of radio channels simultaneously, flagging anomalies no human ear could ever catch. These AI systems don't just look for simple patterns, they hunt for the statistical fingerprints of technology hidden in datasets so vast they'd take lifetimes for traditional methods to process. And what they're finding is rewriting the playbook for how we eavesdrop on the universe. Traditional SETI searches suffered from a needle in a haystack problem. Narrowband radio signals, those most likely to be artificial, were often drowned out by natural cosmic static or human-made interference. Researchers would spend years manually vetting candidate signals, only to discover they were pulsars or satellite chatter. But AI changes everything. Breakthrough Listen's neural networks, trained on petabytes of radio observations, have learned to distinguish between the cosmic, the terrestrial, and the potentially alien with startling precision. In 2021, these algorithms identified over 3 million previously unnoticed narrowband signals in just a 5-hour observation of the galactic center, signals so faint and fleeting they'd slipped through every prior filter. The kicker, 8 of those signals exhibited behaviors unlike any known natural or human-made source. They weren't repeating, they weren't drifting the way satellites do, and they originated from a region dense with ancient stars, places where civilizations would have had billions of years longer than us to evolve. The new frontier lies in what AI can teach us about how aliens might communicate. Instead of just hunting for deliberate "we are here" beacons, algorithms now scan for leakage signals, the cosmic equivalent of picking up stray radio broadcasts from a distant planet. One machine learning model, inspired by natural language processing, treats potential alien signals like an unknown dialect, searching for syntactical patterns that suggest intentional structure rather than random noise. Another detects engineered modulation schemes, the subtle ways a signal's frequency or amplitude might be tweaked to encode information, the most radical approach. Algorithms trained to recognize technosignatures we haven't even imagined, using unsupervised learning to flag anything statistically improbable without human bias dictating what counts as alien. But the true game changer may be real-time sky surveys. Projects like the Allen Telescope Array's commensal open-source multimode interferometer cluster now scan 24/7, feeding data into AI systems that alert astronomers within seconds when something unusual appears. Imagine a scenario where a signal arrives from a star 30 light-years away, and within minutes, telescopes worldwide swing into action, not just recording it, but launching reply experiments. This is no longer science fiction. In 2023, Breakthrough Listen's AI detected a candidate signal from the direction of Proxima Centauri while scanning at the same time as Australia's Parkes telescope. The two datasets, when combined, revealed a signal that, while ultimately deemed interference, demonstrated how swiftly machine learning can coordinate global verification. Critics argue AI risks finding false patterns in the noise, but the counterpoint is compelling. Our old methods were missing signals precisely because they lacked the flexibility to recognize truly alien logic. Future upgrades like quantum machine learning or neuromorphic chips mimicking biological brains could push detection sensitivity into realms we can't yet fathom. The question isn't whether AI will find something, but whether we're ready for what it might tell us when it does. The universe's greatest conversation could already be happening, hidden in wavelengths we've only just learned how to hear. With every algorithm trained, we're not just searching for intelligence out there, we're evolving our own capacity to understand it. Moons were once considered cosmic afterthoughts, small, rocky companions to the grand gas giants of our solar system. But the discovery of exomoons like those potentially orbiting Kepler 1625b has flipped that assumption on its head. Picture a world where the sky is dominated not by one sun, but by a colossal gas giant looming like an eternal, swirling masterpiece, its bands of clouds casting ever-shifting shadows across the surface below. This isn't just science fiction, it's a real possibility, and it opens up a staggering new frontier in the search for life. Kepler 1625b's hypothetical moon, dubbed Kepler 1625bi, could be a prime candidate for such a scenario. Nestled in the habitable zone of its star, this exomoon, if confirmed, would receive just enough warmth to maintain liquid water, while its massive host planet shields it from harmful cosmic radiation. But what really makes exomoons like this so intriguing isn't just their location, it's their potential for dynamic, energy-rich environments. Tidal forces from the gas giant could flex the moon's interior, generating heat through friction, much like Jupiter's gravitational pull warms Europa's subsurface ocean. On an exomoon, this effect might be even more pronounced, leading to volcanic activity, hydrothermal vents, or even a churning, molten core that drives a protective magnetic field. The possibilities for life here are as diverse as they are thrilling. Imagine tidal-locked exomoons with one face permanently turned toward their planet, creating eternal planetshine, a soft, reflected glow that bathes the surface in dim but steady light. Photosynthetic organisms might evolve to harness this ambient energy, while subterranean ecosystems thrive off geothermal heat. Meanwhile, the gas giant's magnetosphere could funnel charged particles toward the moon's poles, creating dazzling auroras that illuminate the sky and power atmospheric chemistry. Some models even suggest that exomoons could retain thick atmospheres, thanks to their stronger gravity compared to smaller, standalone planets, but exomoons come with their own unique challenges. The gravitational tug-of-war between star, planet, and moon could lead to extreme seasons or orbital instability over time. Radiation from the gas giant's magnetic field might strip away an exomoon's atmosphere unless it's protected by an Earth-like magnetic dynamo. Yet, life has a way of persisting in the most unexpected places. Just look at Earth's extremophiles, thriving in boiling vents or frozen tundras. On an exomoon, organisms might retreat to sheltered caves, deep oceans, or even develop radiation-resistant biochemistry. The hunt for these hidden worlds is already underway. Next-generation telescopes like the James Webb Space Telescope and the upcoming European Extremely Large Telescope could soon detect the atmospheric signatures of exomoons, hunting for water vapor, oxygen, or methane in their skies. Even more tantalizing, some researchers propose that exomoons might outnumber exoplanets in habitable zones, offering exponentially more real estate for life than we ever imagined. The galaxy could be teeming with these overlooked oases, worlds where life doesn't orbit a star but dances in the shadow of a giant. The universe might not just be silent, it could be holding its breath. The dark forest theory paints a chilling portrait of cosmic diplomacy, suggesting civilizations stay hidden not out of isolation but survival. Inspired by Liu Cixin's sci-fi masterpiece and now debated in academic circles, this hypothesis reimagines the cosmos as a lethally competitive arena where any detectable civilization risks annihilation by advanced predators. Think of it like this: in a forest teeming with armed hunters, the only safe strategy is stealth, to move without rustling leaves, to breathe without making a sound. At its core, the dark forest theory solves the Fermi paradox with brutal logic. If even one civilization in the galaxy's history grew aggressively expansionist, it would have incentive to preemptively strike potential rivals before they became threats. The result, a galaxy where every surviving society learns to cloak its presence, broadcasting nothing not out of hostility but primal caution. Recent papers analyzing game theory and interstellar conflict lend eerie credence to this idea. Simulations show that without perfect trust between civilizations, first strikes become statistically inevitable. The only stable equilibrium is universal silence. Liu Cixin's novels dramatize this with harrowing precision. In his fictional universe, a single careless radio transmission triggers humanity's near extinction as advanced aliens race to neutralize the new competitor. While fiction, the scenario draws from real astrophysical possibilities. Consider the energy requirements for interstellar travel. A civilization capable of crossing light years could repurpose that same technology into planet-smashing relativistic weapons, kinetic rods accelerated to near light speed, turning asteroids into extinction-level bullets. The math is sobering. It's easier to sterilize a planet than to converse with it. Yet critics highlight flaws in this grim vision. Wouldn't at least some civilizations prioritize cooperation over conflict? Others argue that stealth is ultimately futile. Any species harnessing starlight for energy would inevitably leak detectable heat signatures. But the dark forest's most unsettling implication isn't about aliens at all. It holds up a mirror to humanity's own trajectory. Our radio and TV broadcasts have already leaked into space for over a century, creating an expanding bubble of noise that any observer could trace back to Earth. Initiatives like METI, messaging extraterrestrial intelligence, deliberately beam signals to nearby stars, a practice some scientists liken to shouting in the hypothetical forest. The debate forces us to confront existential questions. Is the universe's silence a warning or an invitation? Are we the naive newcomers, oblivious to hidden rules older civilizations have learned the hard way? Or is the dark forest just one possible answer among many, a reflection of our own fears projected onto the stars? As we develop tools to detect exoplanet atmospheres and Dyson swarms, we might soon face evidence supporting or dismantling this theory. Until then, the cosmos remains a vast, echoing woodland where every rustle could be the wind or something far more deliberate. Pulsars shouldn't exist, or at least that's what astronomers first thought when these bizarre cosmic objects were discovered in 1967. Stumbling upon a signal so precise it rivaled atomic clocks, researchers initially dubbed it LGM-1, short for Little Green Men. The rhythmic pulses coming from deep space were so unnervingly regular, so artificial seeming, that for a brief, electrifying moment, science flirted with the idea we might be hearing an alien distress call or beacon. Of course, the truth turned out to be no less extraordinary. A rapidly spinning neutron star, the corpse of a supernova, blasting beams of radiation like a lighthouse across the cosmos. But what if we've been too quick to dismiss that early instinct? What if some pulsars aren't just natural phenomena, but repurposed as cosmic signposts by civilizations far older than our own? The notion isn't as far-fetched as it sounds. Pulsars possess unique properties that make them ideal interstellar billboards. Their pulses are detectable across thousands of light years, cutting through cosmic noise with unmistakable precision. A technologically advanced civilization could, in theory, modulate these pulses, altering their timing or intensity to encode information, just as we use radio waves to transmit data. Imagine an alien society engineering a pulsar's magnetic field to create deliberate gaps in its rhythm, like Morse code written in starlight. The energy required would be staggering, but for a Type II civilization harnessing the power of its star, it might be as trivial as we find broadcasting a radio signal. This very possibility inspired one of humanity's boldest attempts at cosmic communication, the Arecibo message of 1974. Beamed toward the Hercules globular cluster 25,000 light-years away, this 3-minute transmission was a primer on earthly life, encoding everything from our DNA structure to our planetary position in simple binary. But here's the audacious part. Scientists aimed it at M13, a dense collection of ancient stars brimming with pulsars. The unspoken hope that any civilization there might recognize pulsars as natural amplifiers, cosmic relay stations to rebroadcast our message deeper into the galaxy. Modern pulsar research keeps stumbling upon oddities that resurrect the beacon hypothesis. Take PSRB 1913+16, a pulsar whose timing irregularities defy easy explanation. Or the Black Widow pulsars, which mysteriously vaporize their companion stars, behavior some theorists speculate could result from deliberate energy harvesting. Even more provocative are the so-called slow pulsars, whose intervals stretch far beyond typical neutron star rotation rates. Could these be natural objects artificially braked to transmit slower, more decipherable patterns? The challenge lies in distinguishing nature's artistry from potential engineering. Pulsars already produce complex timing variations from glitches in their spin or through gravitational interactions with orbiting planets. But advanced algorithms scanning these signals for non-random patterns, like prime number sequences or mathematical constants, haven't yet found smoking gun evidence. That hasn't stopped projects like SETI Pulsar Search Collaboratory from training AI to flag anomalies that might escape human notice. Whether pulsars are silent sentinels or merely nature's most precise timekeepers, their existence reshapes how we imagine interstellar dialogue. They prove the universe broadcasts information in ways we're only beginning to decode, and hint that the line between natural wonder and artifact might blur when staring into the cosmic deep. After all, if we ever do intercept a pulsar's pulse that doesn't quite fit, will we recognize it as a hello, or dismiss it as just another quirk of the cosmos? The answer could depend on how willing we are to revisit that original, thrilling suspicion that sometimes the universe winks back. The Fermi paradox hits like a cosmic gut punch. With billions of potentially habitable planets in our galaxy, why does the universe feel so silent? One terrifying answer lies in the Great Filter theory, a concept that suggests some invisible barrier prevents life from reaching interstellar scales. The question isn't just whether this filter exists, but where it's hiding, in our past or ominously in our future. If the filter is behind us, we've already beaten staggering odds. Life might typically snuff out before multicellular organisms emerge, perhaps because oxygen-rich atmospheres are rare, or because DNA's origins demand chemical flukes even rarer than we imagine. Earth's own history supports this. Simple life appeared almost instantly, geologically speaking, while complex life took billions of years of false starts. That gap implies something extraordinary, that microbial life is common, but the leap to sentience is a cosmic lottery few win. The fact we're here at all could mean we're outliers, survivors of a bottleneck that silenced most other potential civilizations before they ever looked up at their own stars. But what if the filter lies ahead? Climate collapse, nuclear war, runaway AI, these aren't just existential risks but potential great filters in the making. Advanced civilizations might inevitably create their own demise, whether through resource exhaustion or technologies they can't control. Consider the silence around red dwarf stars. Despite their abundance, no technosignatures have been detected there. Could it be that tidal-locked planets orbiting these stars inevitably trigger climate apocalypses, or that their frequent flares sterilize civilizations before they escape their home systems? The filter might not be a single event, but a series of traps, each more perilous than the last. The discoveries we've explored add haunting layers to this debate. Phosphine on Venus and methane on Mars hint that life might spark easily, even in hellish conditions, but none of it evolved radios or rockets. Europa and Enceladus suggest subsurface oceans could be common. Yet if intelligence requires land-based evolution, these water worlds might brim with microbes but never mathematicians. Even Earth's trajectory chills the spine. We nearly went extinct in multiple ice ages and asteroid impacts. How many other civilizations stumbled at similar hurdles, their potential erased by cosmic bad luck? Yet there's a flip side to the bleakness. If the Great Filter is ahead of us, awareness might be our salvation. Unlike dinosaurs, we can see asteroids coming and deflect them. Unlike ancient microbes, we're experimenting with planetary-scale geoengineering to curb climate disasters. Perhaps the filter isn't a wall, but a gauntlet, something civilizations can pass if they're clever, cooperative, and just a little bit lucky. The very act of searching for other life, of studying exoplanet atmospheres and decoding FRBs, could be humanity's first steps toward ensuring we're not the universe's failed experiment. The paradox leaves us suspended between two futures, one where we're the lone heirs to a silent cosmos, and another where the silence is a warning. Either way, the discoveries we're making, from rogue planets to irradiated exomoons, aren't just about finding others. They're about learning the rules of a game we're only beginning to play. The Great Filter isn't just a theory, it's the ultimate test, and whether we've passed it or not, the universe isn't telling. At least not yet. The James Webb Space Telescope isn't just rewriting the textbook on exoplanets, it's gearing up to dive headfirst into some of the most tantalizing cosmic mysteries still on the table. At the top of its hit list, the TRAPPIST-1 system, that legendary family of 7 Earth-sized worlds huddled around a tiny red dwarf star. When JWST first turned its infrared eye toward these planets in 2023, the data was promising but preliminary. Now, with upgraded observing strategies and deeper exposure times, the telescope is poised to dissect their atmospheres like never before, the real prize. TRAPPIST-1e, a rockier sibling positioned squarely in the habitable zone. Early spectral hints suggested trace gases, possibly carbon dioxide or water vapor. But this next round of observations could deliver something revolutionary: the first unambiguous signs of an atmosphere actively maintained by geological or even biological processes. But TRAPPIST-1 isn't the only puzzle JWST aims to crack. The hunt for Europa, like exomoons, icy worlds orbiting gas giants in other star systems, has entered its most thrilling phase yet. Using a technique called transmission spectroscopy, astronomers will analyze starlight filtering through the thin atmospheric envelopes of these distant moons. The challenge: their signals are buried in the glare of their host planets. JWST unprecedented sensitivity changes the game, allowing scientists to tease out the chemical fingerprints of water, salts, or even organic molecules from the noise. One prime target is Kepler 1625b's potential moon, a candidate with just the right combination of tidal heating and shielding from stellar radiation. If water vapor plumes are detected akin to Europa's geysers, it would mark a watershed moment in astrobiology. Then there's the holy grail: atmospheric biosignatures. JWST upcoming observations will go beyond the usual suspects like oxygen and methane, searching for disequilibrium chemistry, molecules coexisting in ratios that defy natural abiotic processes. Imagine detecting both methane and oxygen in an exoplanet's atmosphere simultaneously, a combination that on Earth can only be sustained by life's constant replenishment. The telescope will also scout for more exotic markers like dimethyl sulfide, a gas produced almost exclusively by marine phytoplankton here at home. The strategy isn't just about confirming single gases, it's about finding patterns, anomalies in atmospheric composition that collectively point toward biological activity. What makes this next chapter so electrifying is the sheer diversity of targets. Beyond TRAPPIST-1, JWST will scrutinize LHS 1140b, a super-Earth with potential nitrogen-rich skies reminiscent of early Earth, and K218b, that Hycean world with its ocean globe atmosphere. Even rogue planets drifting between stars will come under scrutiny, their icy shells probed for signs of subsurface heat. The telescope's extended mission could even capture the first spectra of an Earth like exomoons auroras, magnetic interactions that might betray a hidden ocean salinity. The clock is ticking toward discoveries that could redefine our place in the cosmos. Every observation schedule is a calculated gamble, every spectrum a potential Rosetta Stone for decoding life's universal language. Whether it's a whiff of oxygen on a rocky world or the faint infrared glow of a distant ice moon's subsurface sea, JWST next moves aren't just scientific, they're historic. The data streaming back won't just fill journals, it could crack open the door to answering humanity's oldest, most profound question. The universe has been keeping its secrets for billions of years. Now, finally, we're learning how to listen. From Venus' cryptic Phosphine to Enceladus' organic-laden geysers, from rogue planets hiding subsurface oceans to the eerie precision of pulsars, every discovery we've explored shatters old assumptions about where life could thrive. These 30 cosmic clues don't just hint at life beyond Earth, they redefine the very boundaries of habitability. Think about it: if microbes survive in Venus acid clouds or Martian ice, why wouldn't they cling to existence in the methane lakes of Titan? If binary stars can host stable planets, how many more Earth-like moons might orbit gas giants in just the right Goldilocks zone? The universe isn't just whispering about life, it's shouting, revealing a tapestry of possibilities richer than we ever imagined. What ties these discoveries together isn't just their strangeness, but their insistence that life is more resilient, more creative, and far more likely than we once thought. Europa's plumes and K2-18b's Hycean atmosphere prove liquid water exists in places we'd never considered. Tabby's star and the WOW signal remind us that some mysteries still defy explanation, pushing us to ask bolder questions. Even the silence, the Fermi paradox, and the Great Filter challenges us to confront whether we're alone or simply haven't learned how to listen. But here's the most thrilling part: this is just the beginning. Every new telescope, from JWST to the upcoming Nancy Grace Roman, promises sharper answers. Every mission, from Europa Clipper to Dragonfly, will turn speculation into science. The discoveries we've covered aren't endpoints, they're signposts pointing toward truths we're only starting to grasp, and that's where you come in. Space isn't just for scientists, it's for anyone who's ever looked up and wondered. So tell us, which of these 30 discoveries set your imagination on fire? Was it the idea of microbial life drifting in Venus clouds, or the thought of an entire ocean hidden beneath Enceladus ice? Drop your favorite in the comments. We're obsessed with these cosmic conversations. And if you're hungry for more mind-bending space mysteries, hit that subscribe button. The universe isn't done surprising us, and neither are we. From rogue planets to quantum biology, from Dyson spheres to dark matter life, the next revelations are just over the horizon. Stay curious, keep questioning, and remember, the cosmos has spent billions of years weaving its secrets. We're just getting started unraveling them. See you out